Hi viewers, I hope all of you are enjoying good health. If you are new to our channel, then subscribe and click the bell icon to get the notification for the upcoming videos. Today we are going to learn about VFD. First of all, what is VFD? Basically, VFD stands for Variable Frequency Drive. A VFD is a motor control device that protects and controls the speed of electric motors by varying the frequency and voltage supplied to the electric motor. There are some other names of a VFD are variable speed drive, adjustable speed drive, adjustable frequency drive, AC drive, microdrive and inverter. Basically, the speed of motor is directly related to frequency. If an application does not require an electric motor to run at full speed, the VFD can be used to ramp down the speed by decreasing the frequency and voltage to meet the requirements of the electric motor's load. Whenever a fresh graduate comes to an industry, the question they mostly ask is how the frequency and volt of AC is controlled, or how does a variable frequency drive work. A VFD has three stages. First one is converter. Second one is DC capacitor bank. Third one is inverter. The first stage converter is comprised of 6 diodes, which allow current to flow in only one direction, same as conventional diode bridge circuit. The direction shown by the arrow is the diode symbol. For example, whenever A phase voltage is more positive than B or C phase voltages, then that diode will open and allow current to flow. When B phase becomes more positive than A phase, then the B phase diode will open and the A phase diode will close. The same is true for the 3 diodes on the negative side of the bus. Thus, we get 6 current pulses, as each diode opens and closes. This is called a 6-pulse VFD, which is the standard configuration for current variable frequency drives. For example, let us assume that the drive is operating on a 480-volt power system. The 480-volt rating is RMS, or root mean squared. The peaks on a 480-volt system are 679. As you can see, the VFD DC bus has a DC voltage with an AC ripple. The voltage runs between approximately 580 volt and 680 volt. The second stage, that is capacitor bank, which can help to get rid of AC ripples in DC bus. This capacitor absorbs the AC ripple and delivers a smooth DC voltage. The AC ripple on the DC bus is typically less than 3 volts. Thus, the voltage on the DC bus becomes approximately 650 volt DC. The actual voltage will depend on the voltage level of the AC line feeding the drive, the level of voltage unbalance on the power system, the motor load, the impedance of the power system, and any reactors or harmonic filter on the drive. The third stage, that is inverter, that converts the DC back to AC to drive the motor. Note that in a real VFD, the switches shown would actually be transistors. When we switch one of the top transistor in the inverter, that phase of the motor is connected to the positive DC bus and the voltage on that phase becomes positive. When we switch one of the bottom transistor in the inverter, that phase is connected to the negative DC bus and becomes negative. Thus, we can make any phase on the motor become positive or negative at will and can thus generate any frequency that we want. So, we can make any phase be positive, negative, or 0. The blue sine wave is shown for comparison purposes only. The drive does not generate this sine wave. As we can see, the output from the VFD is a rectangular wave form. VFDs do not produce a sinusoidal output. This rectangular waveform would not be a good choice for a general-purpose distribution system, but is perfectly adequate for a motor. If we want to reduce the motor frequency to 30 Hz, then we simply switch the inverter output transistors more slowly. But, if we reduce the frequency to 30 Hz, then we must also reduce the voltage to 240 volt in order to maintain the volt over frequency. How are we going to reduce the voltage if the only voltage we have is 650 volt? This is called pulse width modulation, or PWM. Imagine that we could control the pressure in a water line by turning the valve on and off at a high rate of speed. Notice that during the first half cycle, the voltage is on half the time and off for the other half time. Thus, the average voltage is half of 480 volt or 240 volt. By pulsing the output, we can achieve any average voltage on the output of the VFD, and in this way the speed of VFD can be controlled. After studying about VFD, the question comes in mind is why should I use VFD? The answer to this question is as follows. Number 1, if you have an application that does not need to be run at full speed, then you can cut down energy costs by controlling the motor with a variable frequency drive. VE, which is one of the benefits of variable frequency drives. VFDs allow you to match the speed of the motor-driven equipment to the load requirement. There is no other method of AC electric motor control that allows you to accomplish this. We can save energy by controlling speed of a pump rather than controlling flow through use of throttling valves. Energy savings can be substantial. Second one is increase production through tighter process control. By operating your motors at the most efficient speed for your application, fewer mistakes will occur, and thus, production levels will increase, which earns your company higher revenues. On conveyors and belts, you eliminate jerks on startup, allowing high throughput. Third one is extend equipment life and reduce maintenance. Your equipment will last longer and will have less downtime due to maintenance when it's controlled by VFDs, ensuring optimal motor application speed. Because of the VFD's optimal control of the motor's frequency and voltage, the VFD will offer better protection for your motor from issues such as electrothermal overloads, phase protection, undervoltage, overvoltage, etc. When you start a load with AV, you will not subject the motor or driven load to the instant shock of across-the-line starting, but can start smoothly, thereby eliminating belt, gear and bearing wear. It also is an excellent way to reduce and/or eliminate water hammer, since we can have smooth acceleration and deceleration cycles. Fourth one is problems caused by full voltage starters. At the instant of energization, the locked rotor, zero speed, is about 600% of full load R. Running current. This heavy current then drops off gradually as the load breaks loose, and the motor comes up to speed, but causes unacceptable voltage sag on the power system, adversely affecting other loads. It can also cause shock damage and long-term excessive wear on the motor. Using this starting method may force the utility to impose a limit on the size of motors you can use, since across-the-line starting causes problems upstream into the utilities system, creating problems for other customers. The switching surges of abruptly starting and stopping create stress on the motor insulation. Additional benefits of VFDs. In addition to energy savings and better process control, VFDs can provide other benefits. A VFD may be used for control of process temperature, pressure or flow without use of a separate controller. Suitable sensors and electronics are used to interface driven equipment with VFD. Maintenance costs can be lowered, since lower operating speeds result in longer life for bearings and motors. Eliminating throttling valves and dampers also does away with maintaining these devices and all associated controls. A soft starter for motor is no longer required. Controlled ramp-up speed in a liquid system can eliminate water hammer problems. Ability of a VFD to limit torque to a user-selected level can protect driven equipment that cannot tolerate excessive torque. That's all from today. Thanks all for watching the video. If you like video, then click the thumbs up button to encourage us.